Good afternoon, everyone. Welcome to week 7 live session structural dynamics presented by Daniel Bashir from IIT Bandras. So, in last session, that's week 6, we studied about the transmissibility and derived the equations for the same. And in today's live session, we will be solving few problems regarding the transmissibility, and later on we will be studying the deriving the equation for the rotating unbalance, and we will also look into these impulse response functions, direct delta function, and this Dhaumel integral also. And in the later part of the lecture, we will be also seeing the natural frequency and damping from harmonic testers like resonance testing and frequency response curve, half power bandwidth. So the first question for today's session will be a sensitive instrument with a mass of 50 kg is to be installed at a location where the vertical acceleration is 0.1 g at frequency of 10 Hz. The instrument is mounted on a rubber pad of stiffness 14 kilonewton per meter and damping size. The damping ratio of the system is 10%. So we are required to find acceleration that is being transmitted to the instrument, uh, and if the instrument can tolerate only an acceleration of 0.005 g, we have to suggest a solution. For this to suggest a solution, we have to play with the stiffness or the mass of the instrument or the stiffness of the rubber band. And we can keep our acceleration that will be transmitted within the level of 0.005 g. So in order to determine the transmissibility, we have to first determine the natural frequency of the system. So natural frequency of the system will be natural frequency. Omega n is defined as root under stiffness of system and mass of the system and root k by m. And we are given as k in the units 14 into 10 power 3, 14 into 10 power 3, and mass is 50 kgs. Solving it, we will get natural frequency omega n as 16.73 radians per second. Okay, so from this data we will find, we will be finding the frequency ratio omega by omega n. Okay, and one more thing, the forcing frequency, that is omega, that's already given. You will be seeing it from the question. That's clear, it's 10 hertz. Okay, 10 hertz. Here, a sensitive instrument with a mass, this was m, mass of the instrument is to be installed where the vertical acceleration is 0.1 g, and the frequency is, okay, 10 hertz. Forcing frequency omega is 10 hertz. Clear to you people? 10 hertz. And the vertical acceleration, or we can say that u double dot naught, that is the maximum acceleration, okay, is 0.1 g, and everything else is given in the question. One more thing is given there, such that the damping ratio is okay. Omega is 10 hertz, so our frequency ratio phi will be omega by omega n. Okay, so first we have to convert 10 hertz into radians per second. It will be 10 into 2 pi. Okay, 2 pi, and omega n will be 16.73. We already calculated it right now. 6.73. So our frequency ratio is 3.755. Okay, so our equation for the transmissibility in the last live session we derived that transmissibility, that is u double dot naught, that will be transmitted, okay, t, and what is the original maximum amplitude, u naught double dot, okay, that is given by, and it's same for everything, either it will be acceleration transmitted, either it will be velocity transmitted, or either it will be force transmitted. Okay, so you have to use the same concept, u dot naught, you will be here, or it will be P naught here, maximum amplitude of the forcing force that's being applied. Everything is equal to square root of 1 plus twice theta p square and divide by under root of 1 minus p square का whole square plus twice theta p का whole square. Okay, it's actually here also whole square twice theta phi. Okay, one more thing, theta is also given as the damping ratio 10%, that's 0.1. Okay, so we are having all the values, so we will substitute it here. We will get our required transmissibility as uh, transmissibility will be equal to u naught double dot that will be transmitted, and what is actually being offered there, u naught double dot, it will be equal to, when we substitute the values, it will be root under it will be 1 plus twice theta is 0.1 and phi is 3.755 and whole square everything. It is 1 minus phi 3.755 or whole square plus twice 0.1 into 3.755 or whole square. Okay, and we will solve, we will get it as 0.0953. Okay, so from this thing you can clearly interpret that only 9% of the acceleration will be transmitted. Okay, it is 9.5% something. So therefore the transmitted one will be u naught double dot that will be transmitted is equal to 0.0953 times actually which is being offered there. Okay, u double naught, and it's mentioned it in the question, it is there as 0.1 g. Okay, 0.1 g, when we substitute 0.0953 into 0.1 g, it will be actually u double naught t will be equal to 0.00953 g. Okay, this will be the transmitted acceleration. Okay, so you are seeing here 0.00953 is being transmitted, but what is the tolerance limit given if the instrument can tolerate only 0.005 g, so we are in excess of 0.00453 g, so we have to accommodate this 0.00453. So we have to play with either mass of the system or damping of the system. From that we can have we can reduce this transmitted acceleration by increasing the frequency ratio, that is omega by omega n, which requires reducing natural frequency, because what we have to do is solution. So it's a part, so it was a part. So in b part here, what is being transmitted, u double dot naught t is equal to 0.00953 g. It is greater than the tolerance limit. Okay, so tolerance limit, so in order to reduce it, we have to increase phi phi ratio, phi is equal to omega by omega n. Okay, omega by omega n, so which requires omega n to be reduced. So we cannot do anything with the omega because it is actually the instrument which is having that frequency. That's the 10 hertz. But we can play with this omega n with the stiffness and the mass on which it is being mounted. Okay. Uh, so we will mount some mass mb, mounting mass mb on instrument to achieve desired transmissibility. Desired transmissibility. Okay. So omega n dash will be, we will add suppose we will add mb is equal to, we are making trial, we will add 60 kg mass to the instrument already which is having a mass of 50 kg. So total will be equal to 60 plus 50 is 110 kg. So with this 110 kg, what will be the new natural frequency of the system? It will be root under k by m. K is there already, 14 into 10 power 3, and we have a new mass 110 kg, 110. So we are getting this frequency as 11.28 radians per second, and with this we are getting pi dash is equal to omega n dash by omega, new frequency ratio as 5.569. Okay. Since we changed the natural frequency of our system, so the damping will accordingly change now. So we will change the damping ratio now. We will see new damping ratio. First the damping damping coefficient of rubber pad. So C is given by theta twice m omega n. It will be theta is first given 0.1 and initially 2 and mass was 50 and initial omega n was 16.73. Okay, it was 160, 167, 7.3 Newton second per meter. Okay. So new damping ratio will be, so for example we will see same damping for the rubber pad. C is equal to theta dash twice m plus mb. Okay, twice m plus mb omega n dash. When we will calculate theta dash new damping ratio from here, C already calculated 167.3 twice 110 kg is total mass. Omega n is 11.28. So we will get it as new damping ratio 0.0674. Okay. So we got our new phi dash as, here I wrote it here, new phi dash as 5.569, 5.569. New damping ratio theta dash as 0.0674 after putting mb is called 50 kg on instrument. So we will check with these parameters after playing with these parameters what is the transmissibility. So whether it is below the tolerance level or not. If it is not, then we have to do one more trial. Okay. So when we substitute this in transmissibility equation, that is U double dot transmitted divided by U double dot sorry, not this will be not not in the equation under root of 1 plus twice theta phi whole square divided by, so 1 minus phi square over whole square plus twice theta dash phi dash, in fact the whole square, it is theta dash phi dash. So when we are substituting it here, we are getting transmissibility as 0.0416. Okay, and we will get the desired transmitted acceleration 0 to u naught double dash transmitted as, and because u naught dash is double dot is 0.1 g, so it will be 0.00416 g, which is less than 0.005 g tolerance. Okay, so we added sufficient mass to our instrument so that it is so that the acceleration transmitted is within that tolerance limits. Okay, so we achieved the desired transmissibility. Okay, so we achieved the desired transmissibility. Solution is, solution, what is the solution? Add mass 60 kg to instrument. Okay, that's the simple case, the simple and the easiest way to achieve the desired transmissibility. Okay, this was the first question of our session. So moving forward, question number two. Okay, question number two. So one second. So our next question is question number two. An automobile is traveling along a multi-span elevated roadway supported every 30 meter. Okay. So we are having an elevated roadway like this one. This is an elevated roadway supported by we are having it's like this. Okay, we are having it's like this. Okay, it's being supported on these piers. Okay, and these are separated by a distance of 30 meters. The separation distance between them is 30 meters. Okay, so distance from here to distance to the middle point of here to distance to this is 30 meters. Constant distance. This is 30 meter. This is 30 meter. Okay. Now the problem here is the roadway profile can be approximated as a sinusoidal with an amplitude of 8 centimeter and a period of 30 meter. Okay. So the roadway profile we can assume like this. Roadway profile. It has a profile like this sinusoidal wave. Like it is like this up to this point, and after that it is changing the profile like this, like this, and this again here. Then it will go like this. Okay, so for that we can assume the amplitude to be 8 meter. So maximum this one from the middle line, the amplitude of the profile can be 8 centimeter maximum. Okay. So actually, what is this profile is because of long-term creep deflection that has occurred at these points. Okay, so total long-term deflection is 16 centimeter, and we can from the middle line we can assume the maximum amplitude to be 8 centimeter. Okay, and the period is 30 meter. Okay, 30 meter. Hmm. The single degree of freedom system can be we can assume a single degree of freedom system of a vehicle traveling over this profile like this. Basic single degree of freedom system. For example, this is a representation of a typical tire of a vehicle, and it is traveling over it. And we will mount this tire to a single degree of freedom system platform like this. Like this, it is having dashboard because basic mathematical representation of a single degree of freedom system which is having damping and stiffness like this. We will be having mass there. Okay. So mass M, dashpot C, stiffness K, single degree of freedom system. Sorry. Okay. So it's traveling over this profile. Okay, let's assume that. So what's here it is? It's a long term deflection due to creep. Okay. When this vehicle is fully loaded, the mass of the automobile is 1800 kg. The stiffness of the automobile suspension system is 140 kilonewton per meter, and viscous damping is such that damping ratio of the system is 40%. So this is a very highly damped system. Determine the amplitude ut of the vertical motion. So when it will be traveling over this bumpy profile, there will be the amplitude of the vertical amplitude of the motion that will be transmitted to this suspension system. Okay, when automobile is traveling at a speed of 60 kilometer per hour. Okay, then the second part is the speed of the vehicle that will produce a resonant condition. Okay, so we have to see at what speed the resonant condition will be achieved while this automobile is traveling over this roadway. So we have to make another and thing here. For example, we will take the same one, same single degree of freedom system we have to take, and we have to see, we have to take the same single degree of freedom system. So it's here. Okay, so it will be vertical motion will be like this. It is traveling on some bumpy profile like this. Okay, it's like this. Okay, so there will be vertical motion or vertical displacement UG. Okay, and what will be transmitted in this single degree of freedom system of a vehicle ut. Okay, basic things. Okay, so we can do it like this. We will assume the tires are infinitely stiff and they remain in contact with the road all the time while the vehicle passes through this roadway. Okay, then we can assume the vertical displacement of the tires as sinusoidal type. It's very easy. So we can assume ug of t, that is vertical displacement of the tires will be what is the maximum amplitude there, 8 centimeter ug naught sine omega t. Okay, so this is a vertical displacement, vertical displacement of tires because of road profile. Okay, so we assume it this one where we are having amplitude ug naught, as already stated in the question, it is 8 centimeter. Okay, forcing frequency will be omega, forcing frequency omega will be equal to 2 pi by t. Okay, where this time period t will be governed by the speed of the vehicle, forcing time period. Forcing time period t will be equal to the span or the period of this sinusoidal profile L divided by the velocity of the vehicle v. Okay, and the time taken by the automobile to cross the span. Okay, so therefore our this omega will be equal to 2 pi v by L. Okay, so we got the forcing frequency as this thing. First we have to see what is the vertical amplitude, vertical displacement being transmitted to our vehicle. A displacement being transmitted. Okay, so because of dismiss road profile, when Speed of vehicle V is equal to 60 kilometer per hour. Okay, 60 kilometer per hour V is equal to in meter per second 16.67 meter per second. Okay, easy to convert that. So our omega will be equal to 2 pi 16.67 and span is L already 30 meter. Okay, everything is consistent so far, units are considered. Okay, it will be 3.491, approximately 3.5 radians per second. Okay, so our natural frequency of the automobile we can calculate as, because its stiffness was already mentioned in the question, on root k by m. We have it's having heavy damping, heavy stiffness of 140 into 10 power 3 and mass of 1800 kg. Okay, 1800 kg. Okay, it is 8.819 radians per second. So correspondingly, our frequency ratio phi will be omega by omega n. Substituting both the values, we will have frequency ratio as 3.96.396. Okay, so when we are having all the data that we require for transmissibility ratio TR, as we know, I already told you, we can rewrite it for the displacement as well. Transmitted displacement divided by offered displacement, vertical G naught, will be equal to under root 1 plus 2i theta phi over whole square divided by 1 minus phi square over whole square plus 2i theta phi whole square, and we are having a damping ratio of 40%, 0.4. When we substitute all the values, we get u naught t as 1.164, 1.164 ug naught, and ug naught was 8 centimeter. Already I told you, ug naught 8 centimeter. Okay, when we substitute this, we will get transmitted displacement over this vehicle as 8.73 centimeter. So you are getting the point here. So the amplitude of this roadway, or the profile of the roadway, is 8 centimeter. Because of that, 8.73 centimeter displacement is being transmitted to the suspension system of this automobile. And given that the automobile is traveling at a speed of 16.67 meter per second, that's 60 kilometer. So this displacement transmitted is a function of speed. For example, if the vehicle is traveling at a very high speed, this displacement transmitted will be very high. Okay. So A part, we have to do B part also. We have to find the speed of the vehicle that will produce a resonant condition. Okay. Mm, B part. Speed of vehicle, speed of automobile, that will produce resonance. So for resonance, this transmissibility should be maximum. Okay. So we are having uh, so we are having case by conventional concept. So we know that Resonance will occur at omega by omega n is equal to 1. That's frequency ratio is equal to 1. That is natural frequency is equal to forcing frequency. But since we are having very huge damping here, okay, theta is very large. So we cannot have that concept here. So we will have resonance-like conditions here. Resonance-like condition only. uh, Condition only when transmissibility ratio is maximum. Okay. And for that case, transmissibility ratio, that is TR, or we can write TR square is equal to 1 plus twice theta phi whole square, whole, sorry, not whole square, twice theta phi divided by 1 minus phi square whole square, twice theta phi whole square should be max. Okay. So our objective function is transmissibility TR whole square. So we have to maximize it. I only squared this equation. Okay. Squaring both sides, we got that one. This is a simple one. Okay. Twice theta. Theta is very huge. So we have to do with this thing. So if we substitute theta is equal to 0.4, we will have our transmissibility ratio square as 1 plus 0.64 phi square divided by 1 minus phi square over whole square plus 0.64 phi square. Okay, this is the thing. So when we further solve this, this will reduce to 1 plus 0.64 phi square divided by phi power 4, phi power 4 minus 1.36 phi square plus 1. Okay, this is our transmissibility ratio square. So it should be, for transmissibility ratio to be maximum, derivative of transmissibility ratio over whole square with respect to frequency ratio d phi should be equal to 0. Okay, we have to find that one. When we do that thing, we imply this method to this. Okay, so we have d transmissibility ratio over whole square divided by d phi will be equal to phi power 4 minus 1.36 phi square plus 1, and you have uh, 2 0.64 phi, then you have minus times 1 plus 0.64 phi square plus 4 phi cube, just u by v formula, 4 phi cube minus 2.72 phi, okay, divided by phi power 4 minus 1.36 phi square plus 1 or whole square. Okay, so when we will equate this thing to 0, this everything we are having only single variable phi, we will get that value as phi is equal to 0.893, or our forcing frequency omega should be equal to 0.893 omega n. Okay, omega n, which gives us forcing frequency omega is equal to because our omega n is 8 point, here we calculated 8.818 radian per second, so it will be omega will be equal to 7.872 radian per second. Okay, so to have this omega 7.872, what will be our speed here? We are having omega, sorry, we are having omega, we are having L, we are having 2 pi. So what will be the speed? So we can equate it here like V is equal to omega L by 2 pi. So we will get V as omega is 7.872, L is 30 meter, and 2 pi is 6.2 into 3.14. It will be 37.59 meter per second. Okay, it will be like this. So converting it to kilometer per second, V will be equal to 135 kilometer per hour. Okay, you are saying that this speed is very much high than 60 kilometer per hour. Okay, so we can write it speed at which automobile automobile has to travel travel to have resonance like condition. So one point to note here is that we didn't use the concept that omega by omega n is equal to 1 because of the heavy damping of the system. Damping was 40%. So we have to necessarily maximize the transmissibility ratio in order to achieve at the resonance like condition. So at a speed of 135 kilometer per hour, the automobile will experience resonance like condition. These are the two problems that we discussed, and the theory of these two problems was already discussed in last week, week 6. So moving forward, we have this rotating unbalance and impulse response functions, where we will see what is a Dhaumel integral. Okay, take a 5-minute break. So next topic is rotating unbalance. This is also the questions regarding the forced vibrations of single degree of freedom systems, where damping is also considered. This is also an important topic, rotating unbalance. Okay, rotating unbalance. For example, we are having a machine like this, huge machine, and it's lying on a rigid floor like this, which is having some stiffness like this, and the floor is offering damping to this machine also, which we can mathematically show like this mathematical model. Okay, so we are having, for example, this having k by 2, k by 2, and we are having the motion of the machine like this, upwards like this. X of t, degree of freedom is like this, and it's having a total mass m. Machine is having a total mass m. So let's assume that there is a this machine is operating in this way, like there is some motor or some mechanism inside, such that so it's having some. Wait a second. So we can assume it's having some rotatory mechanism inside like this, and some mass is rotating inside at some eccentricity E. So let us take this to be mass m. Okay, so it is rotating like this, and the connection is like this, and this eccentricity is E from the center of gravity of this machine, and its mass is m, and it's rotating with some angular velocity. Okay, let's assume that omega. So it will be going through this angular displacement omega t in time t. Okay, this is the basic thing. So we can have the other things like this: m minus m, mass that is not rotating, mass not rotating. Okay, mass that's not rotating, one thing. Total mass of machine is m, unbalanced mass is uh, a small m, and eccentricity is e, and angular velocity is omega. I told you all the things. So let me write it here also. Total mass of machine. Total mass of machine is m, and mass that is not rotating is m minus m. Unbalanced mass. Unbalanced mass is small m. Eccentricity. Eccentricity is e, and angular velocity t is omega, with which this unbalanced mass is rotating. So we can have the total displacement that this small mass at any time will have. Displacement of m will be x dash of t. Okay, it will be equal to, first it will be having some global displacement, that's x of t, That's as the mass rotates, this whole machine is having some time varying displacement x of t and some vertical displacement. So if we assume like this, at any point of time, for example, this mass m, it is already having some, sorry, so it's already having some vertical displacement x of t, okay, from the center of gravity, and this is omega t angle at any instant of time, eccentricity e. So this vertical displacement will be equal to e sine omega t. So additional to x of t, it will be having one more displacement due to the eccentricity and the rotating mechanism e sine omega t. It will be the total displacement at any instant of time of this unbalanced mass small m. Okay. So from this we can compute the velocity and acceleration. X dot dash of t will be equal to velocity of the whole machine plus e omega cos omega t, and similarly acceleration x double dot dash of t will be equal to acceleration of whole machine x double dot of t plus, sorry, it will be minus e omega square cos omega sin omega t. These two things we deduce it. So x double dash of t will be for mass that is not rotating m minus m, and this acceleration will be for mass small m that's rotating. Okay, so equation of the motion will be like this. Equation of motion will be like this: m minus small m x double dot plus m times d2 by dt square double derivative of x dash of t that we already computed. Okay, so plus it is having some stiffness, so c here damping cx dot plus stiffness kx, and it will be all t, it will be equal to 0. So when we substitute x dash of t d2 by dt square, and this is from equation first. Okay, so we will induce this value, whole value, this whole value we will induce, this whole value we will induce from equation 1. Okay, when we do that thing, we will get the solved thing is mx double dot minus mx square plus mx double dot minus me omega square sin omega t plus cx dot plus kx is equal to 0, or in while writing it properly, it will be m x double dot plus cx dot plus kx is equal to me omega square sin omega t, okay. So this will be the governing equation of the motion for this rotating unbalance. One thing important to know here is f of t here is that the forcing function, that is because of the rotating unbalance having mass m and eccentricity e, is me omega square sin omega t. So this will be playing the role of a forcing function. in this rotating unbalance, where we can have the maximum amplitude of this force P naught as me omega square. So this is the correlation with this forcing function. Hope you are following this. Okay, these things. Next thing is impulse response function. This is just a small thing. It will not take that much time. Im- impulse response function. Impulse response function. So we are having for studying the impulse response function, we have to first understand what we mean by direct delta function. Delta function. Direct delta function. Delta of t. Actually, it's a function which is having unit area. Unit area function. What I mean by that is, I will show you like here. For example, we are having x-axis like this, and we are having a function that's covering the area like this. Okay, so we draw y-axis to this. Okay, so this function is like this along x, along y. It is defined in such a way that it will be minus epsilon by 2. It will be epsilon by 2. So that the total width is epsilon and the height is 1 by epsilon. Okay. So we have where we have a limit epsilon tending to 0. So if you people will be interested in finding the area, so we have area will be equal to 1 by epsilon times, so its width will be epsilon by 2 minus epsilon by 2 minus times epsilon by 2, so we are having total area of 1. So we are getting a very important property of this direct delta function is that if we integrate this function, if we integrate this function 0 to infinity, delta of t dt, it gives a value of 1. Obviously it's having area 1, so it will give a value of 1. So if at any point we will collocate this delta function with any function f of t, delta of, and we are finding it at any point, for example a, delta of a dt, it will give the function value at that point. Okay, f of a, that point. So this will be like this. So we need this to rewrite our governing differential equation. So our governing differential equation is, for example, we are having this one. We will write our forcing function in terms of delta t. Okay. So our governing differential equation mx double dot plus cx dot plus kx is equal to delta of t. Okay. So as area of the impulse is 1, so impulse, that is maximum amplitude of the velocity v naught times m, its momentum is equal to 1. Okay, so we will be having v naught, we can write as x naught dot will be equal to V naught will be equal to 1 by m. So we will be requiring this property. Okay, so for this, we already know that its solution will be like this. X of t. For this, we already deduced the solution. X of t, this is a dampened system, so it will be e to the power minus theta p d t. Not here, it will be p t a cos p dt plus b sin p dt. Okay, so where we define the parameters PD as P times under root of 1 minus theta square. Theta is the damping ratio and P is the natural frequency of the system. K by M. K is stiffness mass of the system. So we are assuming this system to be at rest x of 0 is equal to 0, which implies that if we substitute that in the above equation, we will get A is equal to 0. Okay, so this is equation 2. Okay, 2, and we will be getting from that equation to x dot of t. If we take the derivative once, beta times e to the power minus theta pt, and since a is 0, we can substitute a to be 0. We will get minus theta p minus theta p sin p dt sin p dt plus pd times cos p dt. Okay, this one. So we will substitute our boundary condition x dot of 0 is equal to, it will be actually x dot of 0 will be equal to, if we substitute b, substituting t is equal to 0, it will be e to the power 0 is equal to 1, and it will be equal to minus theta sin 0 is equal to 0 times p, and cos 0 is equal to 1, it will be equal to pd. Okay, equation alpha. Okay, so it will be equal to but x dot of 0 is equal to 1 by m from alpha. Okay, therefore we will be having value of b is equal to 1 by mpd, because this is equal to bpd. Okay, okay, this is the thing. So if we substitute x of t this b value in this a and b value here, we will get 1 by mpd e to the power minus theta pt sin p dt, because a is 0, p dt, so cos will vanish there. So this will be response to impulse function using delta Dirac function, impulse response function. Okay, so this is the impulse response function where we are having a pulse which was having a unit area, only area of 1. Okay, so now we are having a few forcing function like this. So we are having x-axis like this, time axis, and this is our forcing function axis p of t. So suppose our p of t is varying like this, it's having some variation like this, but we can, and it's acting up to a time period. t. So let at assume at any instant of time we cut a very small strip of this forcing function like this one such that it makes impulse response function. That is the area of this strip is unity. So at any time t tau, okay, it was having some value. It will be p of tau will be the value. So its area will be correspondingly equal to what will be the value p of tau into tau, okay, d tau, sorry, okay. So it's at interval tau, but its width we choose in such a way that it is d tau. So it is p of tau and d tau is in such a way that it constitutes impulse response function, okay. Okay, so for this impulse, for this small step pulse, that's the impulse response function, we can write the response as above we deduced, just like this one, okay, x of t. We can write for this one, x of t will be for that one is equal to 1 by whatever will be the mass of system divided by the dampened natural frequency e to the power minus theta p, and it is at t minus tau, okay. Sine, because we are checking the response at time interval t equal to tau, sine pd t minus tau p of tau d tau. Because here we have to add, because here it was 1, we assume it area to be 1, but here the area of this very small infinitesimal force strip will be p of tau d tau. So it will be x of t 1 by mpd e to the power minus theta p t minus tau sine pd t minus tau p of tau d tau. So if we have to find the response because of this entire pulse function from t running from 0 from tau running from 0 to tau is called t, for a response due to full force pulse, we will integrate just about term x of t, we will integrate from uh, t running from, sorry, not t running from, tau will be running from 0 to tau will be running up to time t, up to which the this force pulse is acting, 1 by mpd is p of tau, that is the response at any time interval tau, e to power minus theta pd t minus tau sine pd, sorry, it will not be t minus tau d tau, it will be only p here, yeah, it will be only p t minus tau, okay. So we're having this thing, so we're getting a very beautiful integral. This is known as Dhaumel integral. So this Dhaumel integral can be used to find the response of a single degree of freedom system under their excitation because of a force pulse. What we did is we divided this force pulse into small infinitesimal pulses, and for those very small pulses, we wrote the impulse response function and integrated that impulse response function from time duration tau is equal 0 to the time duration up to which the force pulse exists. That's a simple thing. And we got the Dhaumel integral. And using this Dhaumel integral, we can write the response because of a step pulse, because of a rectangular pulse, because of a triangular pulse, and because of half sine and full sine pulses as well, as we already did in like week 5 using the detailed method for deriving the governing differential equation. So this was all for today. Thank you for joining.